team.
Hello everyone, I'm Shane, machine learning engineer from ELIZA. So obviously I do machine learning stuff. So I started doing deep learning, machine learning probably like 4 or 5 years ago. When I started doing deep learning projects, it always took me a little while to figure out what I need to do to sort everything out. From data processing to model learning, model training, and then inference and deployment. It probably was okay to scramble a little bit for the first couple of times, but the third time I realized, no, I need to be smarter, and I need to find a better way to construct a machine learning project. So since then, I was a big fan. Since then, I have been a big fan of structuring proper pipeline for machine learning projects. And I am going to share my enthusiasm with you today on building machine learning pipeline with some findings from my recent project.
Sorry, we're going to take a quick pause just to make sure it's working. Sorry about this.
We'll just try doing the other. It's all good?
It's back up now.
All right. I think the cable's just a bit loose.
Oh, okay.
Continue.
So yes, join me on the enthusiasm on building machine learning pipeline. And this is me on a typical work day, banging my keyboard so hard and enthusiastically building machine learning pipeline. So how many of you are actively involving in machine learning projects or doing machine learning things? Cool. So as you may know, a machine learning project usually involves a set of data for the machine to identify pattern from or learn pattern from. The data can be structured data, for example, a CSV file with defined columns, or unstructured data, such as text, audio signal, or image data. Then you have your algorithms written in code to instruct a machine to learn pattern from the data. If you blend those two things together, or use your code to run the algorithm on the data, then you will get a model file which can be used to do prediction or identify pattern from the future input data. This may seem very straightforward, but there are actually lots of moving parts involved to achieve the goal here. And today, I'm going to take you on a journey that I have been on to achieve the goal I mentioned above by building machine learning pipelines from different types, such as a task-aware machine learning pipeline to task and data-aware pipeline. Before we have a structured pipeline for machine learning project, all the moving pieces required are like this. So you have to import the data, clean the data, define the data schema, format the data, and then you have to process the data before the model training. And then during the model training, you sometimes output some checkpoints to making sure that the model performs okay. And then you have to validate and evaluate the model before you could serve it or do model inference and then deploy it. So there are a lot of moving pieces here, and it can get a little bit messy. So it would be nice if we could put all these puzzles together like this once, so that you don't have to do it every time during the iterative development process. And that's why we need a pipeline for machine learning projects. A pipeline essentially consists of a chain of processing elements arranged in an order that the output of every element would be the input of the next. So the data or the information can flow from one end to the other end of the pipeline smoothly. And this pipeline structure is actually called Theoretic Acyclic Graph. So there are 3 words in this term. First one is graph. You probably are familiar with it. Graph essentially is a structure consisting of nodes that are connected to each other via edges. The second word is directed. So the connections between nodes have a direction, meaning going from node A to B is different from going from node B to A. The last word is acyclic, meaning non-circular. So moving from node to node via edges, you won't encounter the same node a second time. So data moving from one node to another and no going back. This may sound familiar to you if you are familiar with the tree data structure. Here's a diagram of the tree. It is a graph. It has a root node, and the nodes are connected to each other, and the connection has a direction. Also, there's no cycle in the tree. But one thing, the most important attributes to distinguish a tree from a graph, from a directed acyclic graph, is that each node only has one parent. So there's only one path between two nodes. While for a DAG, or directed acyclic graph, it is a graph, it has a root node, it is connected and directed, and there's no cycle in the DAG either. But each node could have one or more than one parent. For example, this node, you could have this node as its parent, as well as this one. So there can be one or more than one paths between two nodes in a directed acyclic graph. Now we know what a directed acyclic graph is. The next question would be, how do we use it or implement it in the machine learning project? In the context of machine learning pipeline, a directed acyclic graph essentially is a collection of tasks arranged in an order that reflects their relationships and dependencies. And there are different types of such pipelines. And first, there's something called task-aware pipeline. A task-aware pipeline essentially is to kick off the next phase of the pipeline simply just by starting the next component as soon as the previous component finishes. So all the data flow mainly in memory. Now let's have a look at one of my projects as an example. The project is to develop an application for text recognition. And at the beginning of the project, all we wanted is just a lightweight pipeline within the application using existing OCR service. So I have some text data, and then I send those text data to existing OCR service. Then I get a recognized text result back. And then I perform feature extraction on the recognized text to extract the features that required. And then I output those extracted features to a desired destination. And what we would like at the beginning is just to have a straightforward pipeline and easy to get up and running. And the goal is to just deploy the application within a serverless architecture as a serverless function. No database required to store any metadata. Data comes in, goes through this collection of tasks, and then the output gets sent to downstream service. As simple as that. And what we end up using is a library called consecution. Consecution is a Python library that has very easy to use pipeline abstraction, and it provides a system for wiring all the simple processing elements together to form a directed acyclic graph. And it is built with synchronous and single-threaded execution strategies designed to run efficiently on a single core. And also, it is implemented purely in Python, which is convenient for me to deploy it as a serverless function. And here is an example pipeline implemented in consecution. And this graph actually is generated by the library. So we have a log node to indicate the start of the pipeline, and then an import node to import the data or read some data from the cloud storage or data storage, and then process the data. In my case, it just converts the data into images or like a settable format, and then send it over to existing OCR service. Then I extract multiple features such as date or number from the recognized text, and then consolidate the extracted features and then output it to desired destination. And here's how you create the pipeline in consecution. So you have a global state to hold global information, or the information that's useful for all the nodes in the pipeline. And then to create the actual pipeline, essentially you just arrange all the tasks or the nodes in a certain order. So you have like log node, import data node, and process data node in sequence. And then you have extract feature node 1 and 2 in a list, meaning both of them are consuming the data broadcasted from the process data node. And then the output feature node would consolidate all the features and then send a result to a downstream service or a data storage. So why do we need a pipeline abstraction framework instead of just write functions and with class maybe? A pipeline abstraction framework actually helps to write more modular and tidier code. So all the tasks in a pipeline, or each one, is captured in a node class in the consecution library context. And with like a mandatory process function to handle the input and output. And you notice that each process function will have like a push function. Essentially, it just pushes the output of this node to the next node as the input. So the interfaces between the nodes are handled or implemented by default in the framework. And you don't have to do it yourself. And also you could add extra like util functions for each node, for example, the extract function here for extract feature node. The definition of each task is very clear and self-contained, readable, and also reusable. And also the modularity is really helpful for if you have multiple people working on the same pipeline. Because as long as the input and output are defined, the actual implementation and development of each node can be distributed among the team and worked on separately because they are very modular. Without a framework, you may have to write all the functions in one or a few big classes, and then and the definition of each task is not so self-contained or readable or nice. And also it might be a little bit difficult for multiple people to work on the same thing because they're all tangled together. So with the framework, the data flow is smooth or already implemented inside the framework. And the definition of the pipeline structure is very clear and readable like this. So it's very nice and cool. Without a framework, you have to call the functions and then pass down the output in the pipeline to the downstream node. And also the definition of the pipeline structure is not that readable or nice. So it's a little bit messy and confusing. Library framework like consecution actually helped me to achieve the goal at that phase of the project, which is nice. But then, later on, down the track of the project, the team and I realized we have to collect our own data and train our own model using machine learning and deep learning to improve the performance or accuracy of the feature extraction. So, and we also want to use that trained model in production environments as well. That's when things get a little bit complicated. So at that point, I have to consider all the fun stuff when it comes to model training as well as productionizing the trained model. So I have to, I would like to monitor the pipeline running and get a quick notice of its completion or where it fails, if it does. And I want to be able to validate the model used in the application to make sure it is good enough or it performs the same or better than the previous version. And I want to be able to pick it up, the pipeline running, and resume it quickly from the last point of failure or the last stop point. And also, potentially, I have to run this pipeline multiple times and potentially across different locations or servers. And also, I want to understand the output of each task a little bit more and make sure that they are as expected and easy to debug. And also, I may have to train my model and run this pipeline with huge data sets without too much speed compromisation. For example, running on a GPU or other resources. With all these factors considered, I still want my pipeline to be as modular as possible, and the model between training and inference are consistent. So there's a lot of things to worry about and can get a little bit daunting. So at that point, library framework like consecution doesn't suit my need anymore. So what I'm looking at is not just a task-aware pipeline, but a task and data-aware pipeline. Because A task and a data-aware pipeline could store the artifact of every component over many executions of the pipeline, so that I could easily debug if something goes on each component. I could resume the pipeline easily from the last point of failure, and I could also validate the model just by comparing it with like the previously trained or generated one. And also it increases the visibility of the execution progress, because you could see what comes out from each element. With all the factors considered in terms of model training and model productionizing, I decided to give TensorFlow Extended a go. TensorFlow Extended is machine learning pipeline framework that implements a task and data-aware pipeline architecture. So in the previously discussed lightweight framework, essentially the users have to define all the consecution, or most of the consecution works of all the components, and also each the task or functionality of each component. So pretty much they have to build everything from scratch. Well, in TensorFlow Extended, it actually predefines a set or sequence of components that are implemented as a machine learning pipeline, including modeling, training, serving, and deployment management. So it typically includes this set of elements. So data comes in, goes to example gen, essentially just read in the data and split it into training and evaluation set. And then statistic gen to generate statistics from the data set. Schema gen to define or generate a schema or features for your data, a feature format for the data. And then example validator to find anomalies or missing values in your data set. Transform to perform processing or feature engineering onto the data. Trainer to actually do model training, obviously. And then evaluator to evaluate the model or perform the analysis of your trained model. And then model validator to make sure that the model is good enough for deployment. And then pusher to push the model onto a serving architecture. So it's good that the framework laid all these steps for you, so you don't have to implement them yourself or define them yourself, because they are pretty much important steps for a machine learning pipeline. Now for in each component in a TensorFlow Extended pipeline, it typically it actually has 3 predefined subcomponents: driver, executor, and a publisher. The framework defined the driver to query metadata generated from an earlier component from the metadata store and feed it into the executor. And the framework also defined the publisher to take the result from the executor and then update the metadata or the result and write it back to the metadata store. So the data, the input and output of each component are essentially from and going back to the metadata store, which is by default just a database. Now the executor is where all the execution work is done and where the user can define the task and the functionalities of each component. So as the data moving through the pipeline, each component would feed the metadata from the earlier component to the executor, executes the defined task, and then updates the metadata or the result and write it back to the metadata store for later components to use in the pipeline. Now, we have all these components. We need something to put everything together and define the sequence of the tasks or the components to form a pipeline, and also manage its execution. So an orchestrator is needed. An orchestrator provides a management interface to trigger a bunch of tasks and also monitor their executions. TensorFlow Extended also provides you a few options as its orchestrator. And the one that I chose is Airflow, just because I have some experience with it previously. So Airflow acts as an orchestrator for my TensorFlow extended pipeline. It connects all the components together with the Theoretic Acyclic Graph concept, and also it implements the interfaces between each component. And it also provides monitoring features to monitor the pipeline running, continuity features to resume the pipeline from the last point of failure or where it stopped the last time, and also reproducibility to be able to run the pipeline multiple times from any certain point, and also potentially you could set it up in different locations or servers as well. And this is my TensorFlow extended pipeline running on Airflow. It is a screenshot, and you can see all the green boxes just meaning they are successfully run. Today I'm going to focus on a few components that I think are worth mentioning. Import example gen to read in the data or import the data. Schema gen to define the data schema. And transform to perform preprocessing onto the data. Trainer to train the model. And model validator to check if the model is good enough. Now, first have a look at the import example gen and the schema gen. So TensorFlow extended has a component called like import example gen. Essentially just reads in the data from different data sources and then split it into training and evaluation data set. It currently supports CSV file and TensorFlow record. I chose TensorFlow record because it's just more generic across different data type. And here's how you create data features for your TensorFlow record. In my example, it is for I was using the handwritten digit recognition image data. So I have image height, width, and depth, and also an image, the label class for each image, as well as a raw array representation of the image data. And based on the features in the data, as well as the statistics generated from an earlier component called statistics gen, the schema gen actually could try to infer the basic properties from the data features. And this is the example of the schema. So you can see here I have feature name, label, and image raw, and the feature data type, integer for label, float for image raw, and as well as the dimension. So it's 10 for label, meaning from digit 0 to 9, and then 784 for image raw. So it's image height 28 times image width 28. Now, once we have defined the schema and we also have imported the data, it's time to perform preprocessing on the data, which is done in a transform component. Transform component would have a full pass onto your data, a full epoch, and then create TensorFlow operation to apply the preprocessing functions to your data. And in my example, I just apply a normalization function onto my image data before model training. And the transform component would generate a TensorFlow graph containing all the TensorFlow operations. The graph is hermetic, meaning it contains all the information needed to perform the transformation, so that the transformation or preprocessing between training and serving are consistent. Now, once we have transformed our data, the pipeline, which is the input stage of model training, along with the data schema that we defined in the previous step. The model is built, developed, and trained in a component called trainer. TensorFlow Extend mainly supports estimator as their model framework. And here is how you build an estimator. They also provide a very handy function called model to estimator, so that you could convert your Keras model to TensorFlow estimator, which is very convenient because Keras library is very popular among data scientists and machine learning engineers to develop their model. So it's good that you have something familiar with to build your model and then convert it to something that TensorFlow Extended support as the last simple step. And here I use a convolutional neural network for MNIST as an example. One thing to note is that it's better to use TensorFlow Keras library instead of the Keras library directly. Otherwise, the conversion may not work as that well. At least that's in my experience. Now we have a trained model. The next very important step is to make sure that that model is good enough for deployment, and which is done in a model validator component in the TensorFlow extended pipeline. The model validator essentially just checks if the current model performs the same or better than the baseline model, which is the model previously trained with best accuracy. If the current model is the same or better at shooting the right target, then it would get pushed and ready for deployment. If it's worse at shooting the right targets, then too bad, it couldn't make the finish line and it won't get pushed. The one thing that I like about the model file that gets pushed for deployment in TensorFlow Extended is that it is hermetic. It contains all the information for both preprocessing and inference. So you don't need any preprocessing or inference code alongside to run your model in production. And this is an overview of the TensorFlow Extended pipeline. A few things that it might be worth mentioning as a takeaway in TensorFlow Extended is that because sometimes people would find it a little bit lack of flexibility. You have a defined set of components, and also you have limited support starter sources. And also it may take some time to get their head around and be familiar with how it works. But once I went through that learning curve, I found it super useful, and I really like it, because its modularity and standardized machine learning components are very team-friendly. So essentially, you have an unspoken contract or agreement among your team on how to build machine learning pipeline. So the workload can be distributed among the team and worked on separately. And also, I found it has a very well-defined pipeline template for machine learning with important but also easily neglected steps. For example, the model validator, you always hear people say that, oh, this newly trained model works really well on some cases, but worse on the others. So the model validator could actually help to eliminate such a setback. And on the other hand, it uses a generic machine learning terminologies. So it would be helpful for newcomers come to the project and try to learn how machine learning pipeline is constructed. Then they can just go and learn those generic terminologies. To conclude, I have some different use cases for the two example frameworks that I have been discussing in the presentation. So if you are after something lightweight and straightforward, easy to get up and running, and a little bit more generic, then maybe a lightweight library like consecution is a preferred choice. But if you have to run your or train your own model with a complex neural network or with a huge data set, and you have to also deploy that trained model into production, then maybe something more comprehensive like TensorFlow Extended would be a more suitable choice. And that is my journey on building machine learning pipelines.